pleasure to introduce Chris Bishop from Microsoft Research. He found time in a busy schedule to give a talk, which I'm very grateful for. Thank you so much for coming. Without further ado, I introduce here Chris Bishop, who will be talking on accelerating scientific discovery with deep learning. The floor is yours.
Thank you very much. Thank you, Michael, and thank you all the organisers for the opportunity to give this talk. It's rather fun for me, actually, because I first came to Cambridge almost exactly 28 years ago, 1st of July 1997, and it was to run a 6-month programme at the Isaac Newton Institute on neural nets and machine learning. So it's really good fun to be back here on my sort of 28th anniversary. It's also fun for me too because my background is in physics. I did a PhD in quantum field theory at Edinburgh, worked on theoretical plasma physics for the fusion programme for about 8 years, and then somebody called Jeff Hinton got me, distracted me and pulled me into the world of neural computing, where I've been ever since. But for the last 3 years I've been able to bring this arc back together and work on the application of deep learning in the natural sciences, and I believe it's clearly a very exciting field. I think it'll be one of the most impactful areas for machine learning. So I thought I'd begin with the greatest scientific discovery ever made. Now, I thought I might just pause here and give you a chance to think about what would you put on this slide if you had a slide called the greatest scientific discovery ever made. Now, in fairness, I haven't given you a metric. I haven't told you what criterion for being great. So really it's a matter of opinion, I think. But in my opinion, the most extraordinary discovery ever made in the history of science is the fact that our universe can be described in terms of mathematics. And you know, it's not obvious that the universe has to be described by mathematics, but the world around us is described by mathematics. And furthermore, the mathematics is extraordinarily simple. These equations together pretty much describe everything you're going to encounter in your daily lives. And they're very simple. You could put them on a t-shirt. But they're not just some sort of rough and ready description of the world. They seem to describe the world very precisely. Let me give you a famous example, I guess. It's the magnetic moment of the electron. And we can calculate this. We need a couple more equations that weren't on that first slide, but we can calculate this with great precision. And so this is the theory. And there's an error bar there because we've neglected some terms in the perturbation theory expansion, and we can make an estimate of how big they are and put some error bars on this. And then we can go out and measure it. And we can measure it, again, with great precision because it essentially involves just counting. And again, we have an experimental error bar, but you'll see these agree with each other to just extraordinary precision. So these simple equations that you can put on a t-shirt describe the world around us with this incredible precision. The scientific discovery, of course, has really underpinned the evolution of humanity, doubling our life expectancy, changing our lives in so many different ways, and really we're just at the beginning of that. And it's my belief that machine learning, AI, will have a profound impact on scientific discovery. We're seeing that happen already. It's a hugely exciting area. But I want to begin just by thinking about how scientific discovery is different from perhaps other areas where people are using machine learning. And if you think of machine learning, you think of AI, you think of large language models, ChatGPT, and so on. So let's just contrast that with the world of scientific discovery. What makes scientific discovery different? Well, one thing is that in scientific discovery, we're often very interested, for reasons that were clear on the last slide, in numerical quantification. You know, if I want to write an email, I can get Copilot to write an email for me. There's no right or wrong answer. If it's a good email, I'm happy and we're done. If I want to calculate the binding affinity between a small molecule and a target protein for drug discovery, I don't just want a number that looks like it might be a binding affinity. I want the actual number, the number that corresponds to the real world. So quantification and numerical calculation are important. Science at its heart, of course, is an iterative process that involves experiment. Experiment is the gold standard in science. So scientific discovery involves this loop of formulating hypotheses, designing experiments, gathering data, refining our hypotheses, and so on. So that iterative process is very central. If we compare it with the large language model world, then I would say that the data, generally speaking, is very scarce. So in large language models, we can train on sort of the output of human language, of which there is a vast amount, whereas in scientific data, in scientific discovery, data can be very challenging. It could take a PhD student a year just to work out the three-dimensional structure of one biological molecule, for example. On the other hand, sort of compensating for that, is we have the laws of physics. We have a tremendous amount of prior knowledge that we can use to augment the scarce and expensive data. So that leads me to something which I'm guessing most people, I think this is mainly a sort of statistics, machine learning audience for the most part. You're probably familiar with the no free lunch theorem, and it's such a wonderful name. But just let me remind you what this says. It really says that you can't learn just from data. You can only learn from data in the context of some sort of assumption or model or prior knowledge or inductive bias, call it what you like. You have to have some kind of assumption. We'll call it an inductive bias. In the world of large language models, we have very large data. And of course, we have very large models and we need lots of GPUs to be able to train those models. The inductive bias is very lightweight, sort of data-dependent attention, very general prior knowledge, very general inductive bias. For scientific models, on the other hand, we're kind of in the other world. The data is expensive and scarce, as I've said, but we have rich inductive bias. And so that inductive bias can compensate for the smaller data sets. So what do I mean by inductive bias in a scientific setting? Well, I've given an example already, Schrödinger's equation. We'll revisit Schrödinger's equation a little bit later in the talk. But we have these equations that describe the world with this extraordinary precision. So we want to be able to make use of that. We have other properties, invariance, equivariance properties. So consider a molecule. We know that if we compute the energy of the molecule, so how much energy does it take to pull the atoms apart to infinity, as it were, the atomization energy. If I rotate the molecule, that energy doesn't change. Now, in the computer, I might represent the molecule by the three-dimensional coordinates of each of the atoms. So if I rotate the molecule, those numbers are all going to change in a complicated way, and yet the output has to be invariant. So that's a piece of very strong, rigorous prior knowledge. If it has a magnetic moment, when I rotate the molecule, the magnetic moment must rotate with the molecule. That's called equivariance. So this is very different from, let's take the laws of linguistics, the structure of human language that's been worked out for some time. These are really human-created rules, of which there are exceptions and exceptions to exceptions and so on. They're broad descriptions of patterns in natural language. We wouldn't dream of baking those into a large language model. That'd be a bad idea. Neural networks are much better at looking at a lot of language and detecting patterns than humans ever could be. So we don't try to bake that in as prior knowledge. We learn those structures from data. But here, well, we know that these are exact invariance and equivariance properties. And given a scarcity of data, it makes a lot of sense to exploit those. And in fact, this has even led to a whole subfield called geometrical deep learning, which is very, very beautiful, very elegant field. And we have other things too, conservation laws, energy is conserved, mass is conserved, and so on. And so we really want to take those into account as well. I want to give you a perspective that really originated with this person, Jim Gray. He was a technical fellow at Microsoft. He sadly passed away at far too early an age in a boating accident, but he worked on very large-scale compute. He built something called the Terra Circle, which is a bit of a pun because it's a sort of a geographical information model for the planet Earth. Think of it as like a precursor to some of the big models we have today. But he worked on scaling up data science, and he identified a number of different paradigms in scientific discovery, and in particular one he called the fourth paradigm. And so, standing on the shoulders of giants, I want to talk about what we see emerging as another paradigm, another phase shift in the way we can think about scientific discovery, which we rather pretentiously call the fifth paradigm, but if it's a useful way of thinking about it, then I hope it's helpful. So let's just summarize Jim's thinking on this. So the first paradigm of scientific discovery is the empirical, just making observations. So for example, if you draw a line between the sun and one of the planets, then it sweeps out equal areas in equal time. That's one of Kepler's laws of motion. So it's a regularity that we see in the sky, and it's a pattern in nature, and it's purely empirical. And science remained largely empirical really until, appropriately enough, Newton came along, invented calculus, and discovered some of those equations that govern our universe. So really beginning in the 17th century, Maxwell's equations of electrodynamics and electromagnetism. In the 19th century, quantum physics, his Schrödinger's equation again, in the beginning of the 20th century. So this extraordinary discovery that our universe is described very precisely by these very simple equations. Now, these equations are deceptive because they're very easy to write down, but phenomenally difficult, extremely difficult to solve. We can pretty much only solve that for a hydrogen atom using a pencil and paper. And so it really took the third paradigm, the computational paradigm, to unlock the potential of those equations in a practical setting. So with the development of digital computers, beginning in the middle of the 20th century, we saw an explosion of computational science, the use of computers to simulate and solve those equations. The very first use of a digital computer was to solve equations of physics, and that's been one of the most important applications of computers ever since, right up to the present day. But Jim identified at the beginning of the 20th century, of the 21st century, rather, the emergence of another paradigm, also computational but very different, not based on solving the equations of the universe, but instead looking at observational data, empirical data, but at a very large scale. So this is the Atlas detector. It's part of the Large Hadron Collider. It's at CERN in Geneva. You can see a human being in the foreground. This is partway through construction. By the time it's finished, that space is completely rammed full of electronics and detectors and so on. It's built to detect the Higgs particle. I mean, it's just amazing, isn't it? It's like a cathedral to science, extraordinary. And it produced data at just a phenomenal rate, so fast that it couldn't be stored. It had to be filtered and triggered in real time, and most of it thrown away in real time, such was the sheer scale of data. So that's one example of many. So this is data-intensive scientific discovery, the fourth paradigm, based on huge quantities of observational data. What we're seeing now emerge is what we call the fifth paradigm, AI-accelerated scientific discovery. These paradigms don't replace each other. They all remain valid. They build on and augment each other. And this builds on both the theoretical and the computational. So we're now going to leverage those known equations, but instead of using a computer to try to solve Schrödinger's equation, let's say, every time we want to predict the properties of a new material, a new molecule, instead we're going to do something different. It's a mindset shift. We're going to use that ability to solve this equation, we call that a simulator, not to solve the problems we're interested in, but instead to generate training data. And we're going to use that training data to train machine learning systems. So we can call that a surrogate, if you like, or a deep learning emulator. So if we're successful, that trained neural network can now emulate the system of a computer solving Schrödinger's equation. So it's expensive because we have to use a lot of compute solving Schrödinger's equation lots and lots of times to generate the training data. Then we burn up some more compute training the deep learning system. Finally, when we've got the deep learning system, it's now pretty fast because applying new inputs, you get new outputs. It's just a function call, so it's very fast. This makes sense if you're going to use it many, many times. If you're going to use it millions of times, you amortize the cost of generating the training data and the cost of training a deep learning model. And there are many situations where you can do that amortization, and it's very impactful. And a big advantage here is that it's very much faster. Instead of the complex iterative numerical solution of, let's say, Schrödinger's equation, you've now just got a function. It's many orders of magnitude faster. So we can summarize the fifth paradigm as training on synthetic data generated by simulation, that is, by numerical solution of the known laws of physics. The data is perfectly labeled. I'm sure you all know that in machine learning, labels can be a challenge. In the early days of trying to recognize objects in images, it's very easy to get lots of images. Then you had to get some people to sit down and sort of label the different objects. The labels are expensive. The data here is perfectly labeled. It's a computer simulation, so we can measure anything. that's happening in our simulation. We don't have to worry about intellectual property, privacy, GDPR. This is not somebody's personal healthcare data or their DNA records or whatever. These are solutions to the equations of physics. And the quantities, there's no limit to how much of this data you can create. It's really only limited by your compute budget. I say only, of course, it could be expensive and it could be a real limitation. But in principle, you can always just carry on gathering more and more data. And as I've highlighted already, a big advantage of the fifth paradigm is this massive acceleration. And for pretty much everything you try, you get an acceleration that's at least 3, and with a little bit of effort, 4 orders of magnitude, with no loss of accuracy, and sometimes it's more. And you know, we live in a world of millions, billions, trillions. Somebody says, oh, it's 1,000 times faster. Well, do I really care? It sounds boring. I sometimes give the analogy of, imagine if that $100,000 sports car could be yours for $100. Would that make a difference to whether you bought one or not? Well, probably it might do. Maybe don't like sports cars, but you can see a factor of 1,000 or 10,000 can be enormously disruptive. So let me give you an example. That's an example where it is indeed disruptive. So this is modeling the Earth, modeling the atmosphere, modeling the oceans. And so my team in Microsoft Research, called AI for Science, recently published a model called Aurora. And Aurora is the world's first foundation model for the Earth system, the system of the atmosphere and oceans. So this was published in Nature a couple of months ago. And it's a nice application for the fifth paradigm because the way weather forecasts work, when you go to your phone and get a weather forecast, that's based on a thing called numerical weather prediction. So for the last few decades, weather forecasting has been done by supercomputers solving fundamental equations, equations derived from Newton's laws of motion, called Navier-Stokes equations that describe the flow of fluids and other physics that happens in the atmosphere and in the oceans. Those equations are solved numerically on a supercomputer. And it has to be a supercomputer because you need good spatial resolution to get accuracy and good temporal resolution, but you have to simulate it. You know, the real weather is evolving as well. You have to simulate faster than reality because you have to get out ahead of reality, otherwise you don't have a forecast. Nobody cares to look up yesterday's weather, they want tomorrow's weather. So it's a job for a supercomputer, and so there are big centres, the UK Meteorological Office, European Centre for Medium-Range Weather Forecasting, and so on, organisations around the world running big supercomputers, doing these simulations every few hours, launching off another huge simulation, all the time solving those fundamental equations and generating data. Now, the mindset shift says, well, that data doesn't just become obsolete when it's, when the real weather is caught up with the simulation. That historical weather can be used to train a machine learning emulator. And so quite a few people have done this. What's different about Aurora is that it's a foundation model. So instead of emulating a specific simulator, instead, this was trained on very diverse data in order to try to force the model to understand the dynamics, in general, the dynamics of the atmosphere and the Earth system. And because it's a foundation model, it can then be fine-tuned. So for things like ocean waves or tropical cyclones, or in this example, pollution flows. So we're interested in the flow of pollution, like nitrogen oxides around the atmosphere. The amount of data on that is pretty sparse. So look out the window, you'll see pretty much every building has some little weather station on it. The weather data is very rich, very fine-grained. Pollution monitoring, that's much sparser. If all you have available is the pollution data, then you have very little data on which to build models. But if you first build a foundational model of the Earth system, then you can fine-tune it using a small amount of pollution data, and you obtain new state-of-the-art accuracy in modeling pollution flows. So, but it also does pretty good weather forecasting. So this can forecast, it can produce the UK 8-day weather forecast in 1 minute running on a single A100 GPU. So think of that as 3 to 4 orders of magnitude acceleration compared to running a supercomputer. So this model and models like it are really disrupting the way people think about things like weather forecasting. Now this fifth paradigm is very general, very broadly applicable. For the rest of this talk, though, I'm just going to focus on the molecular scale. And the reason is this is I think maybe one of the most important areas for AI for science, because first of all, everything around us is made of atoms, including our own body. The space of possible new configurations, stable configurations of atoms, is gargantuan. Nobody really knows how big it is. It's been quite well characterized for small drug-like molecules, where it's about 10 to the power 60. Something like the number of atoms in the solar system or something. It's a big number. For stable molecules and materials in general, it is some gargantuan number. It's a vast space, and somewhere in that space will be all sorts of interesting new therapies, materials. It's an extraordinary space to go explore, but it's vast, and so we need to explore it efficiently. So multiple orders of magnitude acceleration become extremely valuable. So the timing of this talk is also really very good, because we had a project, we started a project about 3 years ago, and last Wednesday we published the very first paper on this project, so I'm actually able to talk about it today. So the rest of the talk, I've rewritten it over the weekend, and I'm not going to talk about the stuff I was going to talk about in drug discovery and all sorts of other things. I'm going to tell you about these new results. But before I do, I'm just going to show you one example from material science, which is a model called MatterGen. And I included this because I had a very nice talk just before tea break on diffusion models. This is a nice application of diffusion models. But it's diffusion models not to create, let's say, an image, but to create a new crystalline material. So this is what the diffusion looks like. So this is denoising an initial random crystal. So it's denoising the choice of atom type. No, I don't want sodium, potassium, lithium. It's denoising the unit cell, the 3 vectors that describe the unit cell. That unit cell repeated in all directions in a periodic crystal. And it's denoising the continuous locations of the atoms within that unit cell. And it's trying to produce a material that would actually be stable. If you position the atoms in that way, in those positions in that unit cell, that should be a stable material. But as you heard, we can, as well as using diffusion models to generate new instances, we can condition on desired properties. So it could be a text prompt for an image, or here it could be conditioning on the magnetic or the thermal or the mechanical or other properties of the material. So condition on the desired properties of the material, and then run the generative model in order to produce the desired material. So this is just a rather nice illustration of different materials produced by MatterGen, where each one has been conditioned on some desired physical properties. Now, when I talked about emulators, an emulator can calculate the properties of, say, a new material with the same accuracy as a simulator, but 3 or 4 orders of magnitude faster. So think of that as a way of taking a haystack and be able to sift through the bits of hay 10,000 times faster to try to find that needle. MatterGen is, if you like, complementary to that. This tells you where in the haystack to go look. You're looking for a better magnet with, say, less lithium, or battery with less lithium, or a stronger magnet, or whatever it might be. This is able to generate candidate materials very quickly, and therefore replaces what otherwise might be a more random search with now a more focused search. That's probably worth another 3 to 4 orders of magnitude as well. So it's still a vast space that we're trying to search, but acceleration by multiple orders of magnitude is extremely powerful. So that was a brief overview of MatterGen. What I want to do now is to spend the rest of the time talking about some work that we published last Wednesday. This is a project that we started 3 years ago when we launched the AI for Science team, and it relates to a piece of science that's sometimes called the most important piece of science that you've never heard of. It's called density functional theory, or DFT. So just like a show of hands, put your hand up if you know roughly what DFT is. Oh, okay. That's, I think 10 or 15% of you. Great, okay. Well, in the next half an hour, you're going to learn a lot more about DFT and why it's important. But I'm going to begin by talking about Schrodinger's equation and wave functions. So Schrodinger's equation is a partial differential equation that describes a quantity denoted by psi, which is the electron wave function. This is a complex function of the positions of all the electrons in the molecule. So x1 to xn are the spatial positions of the n electrons. And the square modulus of psi describes the probability density. So that's the probability density of finding electron 1 at position 1, electron 2 at position 2, and so on. And so when we solve Schrödinger's equation, we're solving for psi. And once we have psi, we can then calculate any quantity of interest. Now, solving Schrödinger's equation, as I said earlier, is extremely difficult. Very easy to write it down, extremely difficult to solve it. Let me give you some intuition as to why it's difficult. The problem has to do with the fact that it depends jointly on all of those electrons. So this is the caffeine molecule, which has 24 atoms. The nuclei are held together by a cloud of 102 electrons. So each electron, the position of each electron is described by a point in three-dimensional space. So psi, for the caffeine molecule, it lives in a space of 306 dimensions. So a very simplistic way of solving Schrödinger's equation, it's a partial differential equation, continuous variables. We could discretize the space. So we could divide the space up into a grid and then replace the partial derivatives with finite differences and solve numerically in the usual way. And as you can appreciate, the number of grid points grows exponentially with the dimensionality of space. So when we're doing atmospheric modeling, we're solving in a three-dimensional space, or even a kind of a 2.5-dimensional space. But here we're working in a 300-dimensional space. So you can see that a naive approach based on simply carving things up into a grid would be completely out of reach for anything other than a very, very tiny molecule. Now, if you actually want to solve Schrödinger's equation, there are much more sophisticated methods than just creating a grid, but the point remains that the exact solution of Schrödinger's equation has a computational cost that grows exponentially with the number of electrons. So I think this could be nicely summarized. The challenge here can be summarized, has been summarized as follows. The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are completely known, and the difficulty is only that the exact application of these laws leads to equations much too complex to be soluble. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. So that's the fundamental challenge. And what's interesting is that those words were written by Paul Dirac nearly 100 years ago, and Dirac's statue, or bust at least, is outside in the foyer of the Newton Institute. He was a professor of mathematics at Cambridge. So that's really been the journey of quantum physics for the last 100 years, tackling that fiendishly difficult exponential cost of actually solving Schrödinger's equation in a practical setting. Now, it's not just a case of wanting to solve it quickly. We need to tease this apart and understand a little bit more carefully what we mean. And really, it's a trade-off between three things. We call it the fundamental trilemma, between accuracy, speed, and generality. We need a method that is sufficiently fast that it's affordable, has to be sufficiently accurate that it's useful, but it needs to be general. It's no good if we've got a fast, accurate method that only works for the caffeine molecule. We need something that can generalize to new molecules, new materials. And the important criterion here for accuracy is something called chemical accuracy. Chemical accuracy is generally considered to be about 1 kilocalorie per mole. Slightly strange units, but the point about chemical accuracy is that, roughly speaking, if you can make a computational prediction to chemical accuracy, then you become predictive of experiment. And that allows you to think about shifting the world of scientific discovery of materials and molecules out of the laboratory and into the computer. So this is a sort of a gold standard, something we're really striving for. Chemical accuracy, if we have systems that can reach chemical accuracy, this can be transformational, because instead of the very slow, very much laboratory-based iteration through that scientific cycle that we talked about at the beginning, instead it becomes possible to do much of the heavy lifting computationally. We'll always do experiments, because experiments are always the gold standard, but it should be experiments to verify the results of computation. And it's challenging because we need to do this with high precision. The difference between a molecule existing and just falling apart, for example, is a relatively small change in the energy. The quantities that we need to calculate need to be calculated with high precision. So an analogy that's sometimes used is, imagine you're trying to find the weight of the captain of the ship. One way to do it is to weigh the ship with the captain, weigh the ship without the captain and subtract them, and mathematically that is equal to the weight of the captain. But for that to be successful, you would have to compute the weight of the ship very accurately to very high precision. So that's sort of analogous to what we're trying to do here. So, 100 years have gone by since Schrödinger's equation. Lots of very smart physicists have thought about this, and a whole bunch of methods have, in fact, a whole field called quantum chemistry has been developed. And there are lots of methods. I'll mention one of them. It has a snappy title. It's called coupled cluster, single, double, perturbative, triple. And it's able to achieve chemical accuracy on a number of systems. But it's an approximation, and it's an approximation that scales as the 7th power of the number of electrons. So that's a big improvement over exponential, but it still, again, really limits us to very, very small systems. Of course, there are other approximations that have much better scaling, but their accuracy is correspondingly much poorer. So we're all a bit stuck, really. At least we were stuck until a remarkable breakthrough was made in 1965 by Walter Kohn and others, and it's called DFT, or density functional theory. And what Kohn showed is that we don't need to actually calculate the full wave function. Instead of working with this horribly complicated object, the wave function, we can work with a much simpler thing, which is just the electron density. Just the density, the charge density in space, just a function of 3 coordinates. So it's a much simpler object to work with. And while computing the wave function has a cost that's exponential in the number of electrons, the cost of calculating the density in density functional theory grows only cubically the number of electrons. So this is a much more practical method. Now you may say, well, so what's the big deal? You know, people are always finding different approximations, different costs, and so on. The big deal is that this is exact. That's an extraordinary result. Instead of solving Schrödinger's equation, we have to solve a set of equations. So that result was, I think, 1965. I think the following year, Kohn and Scham turned this into a practical scheme by developing the Kohn-Scham equations, self-consistent field equations. These are iterative equations, essentially one function, one orbital per electron, and they're solved self-consistently. So you make some initialization and then you iterate these coupled equations. And those equations have a cost that's cubic. But the density functional theory scheme is exact, which is really quite remarkable. Again, if you like little analogies, I always think the analogies, you probably remember these more than you remember the equations, but one way to think about it is like this. So imagine that 3-dimensional plastic molecule object. That's like the wave function. It's something really, really complex living in a high-dimensional space. And getting at it and understanding it's very hard, very difficult. But it turns out we don't need it. All we need is kind of a shadow, a low-dimensional shadow of the wave function, which is the electron density. That turns out to be sufficient, and we can compute that much more easily. So this result, that we can go from exponential to cubic, is so extraordinary that it earned Walter Kohn the Nobel Prize. He won the Nobel Prize in chemistry. It was awarded in 1998 for the development of density functional theory. And since then, it's been pretty much the only show in town. So today, if you want to calculate something to do with molecules, materials, and so on, you're pretty much going to turn to density functional theory. And that's why it's sometimes described as the most important thing in science that you've never heard of. It's probably the most highly cited thing in the history of science. Here you can see citations, because it's not just maybe the small community of people working on DFT itself that are citing these papers. It's the armies of people doing practical stuff every day in academia, in industry, in drug discovery, in materials design. Thousands and thousands of people every day using density functional theory. And here's a little graph. I think this relates to UK supercomputer usage, but it's the breakdown of supercomputer usage by different sectors, and you can see that density functional theory is a very large slice of that pizza. So it's a very practical and very widely used method. Okay, so at this point you're thinking, hang on a minute, what's the catch? We've taken this exponentially hard problem, we've made it, we can solve it exactly in cubic time, huge practical, are we done? Didn't quantum physics end in 1965? What's the catch? Well, the catch turns out to be really interesting. So I said that instead of solving Schrödinger's equation, we solve these self-consistent field equations called the Cohn-Sham equations. The Cohn-Sham equations have a term in them called the exchange correlation functional. Now, the exchange correlation functional turns out to be universal. So it's the same functional for caffeine molecule, for diamond, for everything, for all molecules, all materials, all assemblies of atoms. It's the same functional. So it's universal. But unfortunately, Cohn, and nobody since, has ever written down a mathematical form of the exchange correlation functional. It's sometimes defined as the difference between a certain model for the energy in the Cohn-Sham scheme and the exact energy. In other words, it's like you've taken all the bits you didn't know and lumped them all together in a thing, given it a name, exchange correlation functional, and you're no wiser about what really is inside there. You know it's universal, but we don't know what it is. So this is kind of a 60-year-old grand challenge of science. It's an extraordinary mystery. We know it exists, we know it's universal, nobody's been able to write it down. So how do people use DFT in practice then? What are all these thousands of people using DFT in practice? Well, they're using one of these handcrafted functionals. I think there's at least 800 of these now. It's sometimes called the zoo. This zoo of handcrafted functionals where people have written down, using intuition, guided by some laws of physics, guided by some empirical studies, they've written down their favourite sort of approximation to the exchange correlation functional. Some of them are useful for small molecules, some of them are useful for crystals, none of them is universal, and none of them is exact, and they have various varying computational cost. So we find ourselves back in that world of trading off speed and accuracy. There's something called Jacob's ladder. It's this, I think it's a biblical term, but it refers to the idea that these functionals can be ordered as a sort of ladder, and on the lower rungs of the ladder, you have very cheap approximations, things that scale cubically, wonderful, but they're not very useful in practice because the accuracy is low. As you go up the ladder, you get more and more sophisticated functionals, particularly ones that capture non-local effects. They become more accurate. But the cost of calculating the functional can now be n to the fourth, n to the fifth, n to the seventh. And you're back into the world of bad scaling because your approximation has this bad scaling. So that's called the Jacob's ladder. And a few years ago, let's see, I'm thinking, yes, 2022, 3 years ago, this paper was published in Science called In Pursuit of the Divine Functional. And it was really talking about this open challenge. This universal functional exists. Nobody's ever been able to write it down. We've got all these hacky approximations, none of which is really completely satisfactory. Is there some way to find this divine functional? And of course, could we use machine learning to learn the functional? So that would be a nice thing to try. So first, though, let's just summarize where we are today in density functional theory. So on this graph, the vertical axis is the error. So we want error to be as small as possible. It's in units of kilocalories per mole. So that blue strip along the bottom is chemical accuracy. That's where we want to be. We want to be living in chemical accuracy. And along the horizontal axis is the cost of running density functional theory with these different approximations. And you can see this sort of Pareto curve going top left to bottom right. We've got some cheap, even some n-cubed functionals, but the accuracy is terrible, far too low in accuracy, far too high in error to be predictive. At the high end here, n to the fifth, we're starting to approach chemical accuracy, but these are getting very expensive. And so that's kind of where DFT is today. So The goal, of course, is to find something that has chemical accuracy that scales as n cubed, and that was the sort of promise held out by Walter Kohn in 1965 and has eluded us for the last 60 years. So what about machine-learned exchange correlation functionals? A lot of people have been trying this, I mean, for a good number of years. Nothing of practical value has yet emerged. One reason is that, one of the main reasons, that previous approaches have used handcrafted features. In other words, they've taken the kinds of features that people use in that Jacob's ladder, but combined them using machine learning. And the problem then is that to get high accuracy, you need some of these more non-local features. They get expensive, and so you end up with a machine-learned functional that, again, is too expensive. So what we've done is to approach this afresh and to say, if we're going to use deep learning, we have to get away from handcrafted features. We have to be able to learn the function from data. It's rather analogous to, you're familiar with computer vision. Before the development of deep learning, people used machine learning to do computer vision, label the objects in an image. But a lot of effort went into devising handcrafted features. If you're in this field, remember SIFT features are very popular. These sort of complicated features, hand designed, have to be calculated first, and then machine learning kind of combines them together in some learned way. Deep learning blew all that away. The deep learning, you start from the pixels and you learn all the internal representations in a deep hierarchical representation. So we want to do something analogous, but that's going to need data on a different scale from what's been available previously. And so for much of the last 3 years, we've been building a data set of, based on 150,000 molecules that's 2 orders of magnitude larger than, has been available previously. And that's been crucial. We're restricting attention to so-called main group elements. So we're looking only at molecules, not at periodic systems. And we're just looking at if you know your periodic table, it's sort of the left-hand side and the right-hand side. There's that big block of transition metals in the middle that we're not yet considering. So just looking at main group metals. And we need labels, and the labels come from those expensive quantum chemistry calculations. Remember, coupled cluster methods, n to the 7th. So it's a data set that's 2 orders of magnitude bigger than anybody's produced before. It's required both a huge amount of compute, but also a lot of human expertise as well. Because not only are these wave function methods, these accurate wave function methods, not only very expensive, but they require a lot of human expertise to guide them. They're not just automated programs that just run. They need a lot of human expertise to guide them. But we have two good things on our side. Remember that the need to balance data with prior knowledge. So we have, of course, we want to generalize to large molecules, and already begin to see some of the paradox here, because I've just said, well, we're going to generate the training data using these expensive wave function methods that I've already said are impractical. It's only going to work if we can generate data for smaller molecules and then generalize to larger molecules. And the two reasons why we may be able to do that are the self-consistent field and the exchange correlation universality. I'll mention that again in a moment. So we call our model Scala. So Scala comes from the Greek, meaning ladder, and it's a fast ladder. So this is the world's first deep learned exchange correlation functional that's able to achieve high accuracy, and it doesn't sacrifice speed. So the goal is to get from the exchange correlation functional as a thing that takes the electron density as input and produces an energy as output. So from the electron density, there's some big terms, Hartree energy, kinetic energy, and so on. These are things we know how to calculate. And they can be calculated cheaply. And they're, if you like, the ship rather than the captain. So they give us most of the energy, so we know how to do that. But we need this extra piece, the exchange correlation energy. That's really critical. Without that, we get terrible results. And so we have a machine learned system that goes from the electron density to the exchange correlation energy. And here non-locality is learned, but it also has to be scalable. It has to work for larger systems. And part of the way this is done is through a message passing scheme. So it's usual to represent the electron density as a point cloud. The point cloud may have, 1 million points. This achieves scalability by using a coarser point cloud for example, the centers of every nucleus of every atom in the molecule, and then doing information gathering from local fine points to the coarse points, aggregating that information, then passing that information back out to the fine points. If you're familiar with graph neural nets, you'll be familiar with that sort of type of message passing scheme. It's a complex and difficult machine learning problem. One reason is that the wave function methods give you the energy. They don't give you the exchange correlation energy because they decompose the energy in a different way. So another challenge is that exchange correlation energy, that functional, sits within an iterative scheme. It sits within the cone-Sham scheme. So it's a more complex and in some ways more interesting machine learning model than just a simple regression. So here are some of the results. This is the two axes both represent error in kilocalories per mole. The bottom one is for a couple of well-known, widely used benchmarks. One of them on the horizontal axis is main group chemistry, general chemistry, and then the vertical axis is the specific task of atomization energies, the energy to break a molecule apart into its atoms. And you'll see that on atomization energy, it reaches chemical accuracy. And on general chemistry, if you look carefully, you'll see the circular, the circles here represent, so these points here are standard density functional theory functionals. The circles represent ones with cubic scaling, and you can see it outperforms, in terms of error, it outperforms the ones with cubic scaling, and it's pretty competitive with these which have fourth power scaling on general chemistry, and outperforms everything on atomization energy. So I think a really exciting result. I think perhaps the most exciting thing, though, is to me this feels like it sort of shone a light on the path. This is not yet the universal exchange correlation functional. It's restricted to main groups, it's restricted to molecules, but I think it does, for the first time, I think, shine a light on a path that could take us to a model of the universal exchange correlation functional while preserving speed and yet achieving chemical accuracy. If that's true, I think it'll be a very exciting scientific result. This is a problem that's been outstanding for 60 years. But I think perhaps even more importantly, this could open the door across fields like material science, drug discovery, to be able to do predictive calculations in the computer, to really shift things from the laboratory, which is slow and expensive, into the computer. I think that could be transformational. So we're very excited about this. So I'm pretty much done. Hopefully there's time for a few questions, but I'm going to begin by asking a question myself, because it's sort of an obvious one, and it's a very important one. So just to remind you, what we did is we took 150,000 molecules and we solved Schrödinger's equation using these coupled cluster, very expensive coupled cluster wave function methods to produce accurate energies. And then we use that to learn an exchange correlation functional, which sits inside this iterative cone-Sham self-consistent field. So now, given a new molecule, what do you need to do? You need to run the iterative n-cubed cone-Sham scheme using the Scala functional. It's a bunch of compute. Why go to all that bother? You've got a bunch of molecules which have got the molecular structure and the desired energy. Why not just learn a regression? Why not just treat that as a training set and train a neural network to take the molecule as input and produce the energy as output? All this cone-Sham stuff, forget all of that. This is, why not do that? It's a great question, and the answer is you can. And it's usually called a machine learning force field. It's called a force field because if you take the gradient of the energy with respect to the nuclear coordinates, you get the forces on the atoms, and you use those for things like molecular dynamics and so on. So it's an energy field or a force field. Its advantage is speed. Right? It's now just like the emulators we talked about before. It's just a function, and so give it a new molecule, and then in finite time it will just calculate the energy or other properties. Force fields are machine learning force fields are very widely used in AI for science. They're almost like the bread and butter of the field. We've trained a bunch of them in my team. Hundreds or thousands of them have been produced. They're very useful. They're very widely used. The disadvantage, and the reason we don't do that, is generalization. Right? Remember that third axis of our trilemma. We want to be able to generalize. Why do we think this can generalize? Well, we think it can generalize because we've baked in a lot more physics. This is not just sort of curve fitting to a set of data. It's not just a regression on the data set. Instead, first of all, we know that the exchange correlation function is universal. So we hope that learning something about the exchange correlation function over some part of molecular space will generalize to other parts of molecular space because it's a universal function. The second thing is by learning the exchange correlation functional and embedding it within the Cohen-Sham equations, those Cohen-Sham equations already contain most of the physics. Remember I said, there's some big terms in the energy contribution that we can calculate efficiently and accurately. And the exchange correlation term is like the final piece. Well, being able to do most of the heavy lifting using this exact physics is going to make the job of the machine learning a lot easier. It's like trying to predict the weight of the captain instead of trying to predict the weight of the boat plus the captain, roughly speaking. And we do have evidence of that generalization is happening, so we're very excited about that. Then we could do something even more. So you can imagine the following. You can imagine now running DFT with Scala, not to predict the properties of the next molecules and materials that you're interested in, but instead to generate training data to train an emulator. So now you have this very elegant hierarchy that's really leveraging a great deal of known exact physics. DFT with Scala, n cubed, it'll be cheap. Instead of generating 150,000 molecules, we could generate millions and millions of molecules over some desired region of chemical space, and then fit those results using a neural network to have a machine learned force field that will be fast and accurate over some new region of chemical space. So it might be that's how we end up using this, not directly by solving Cohen-Sham, but again by applying the fifth paradigm at this second level of the hierarchy, generating big training data sets and learning fast machine learned force fields. A big thank you to the team. This is just the core team. There's a much larger number of people involved in this. Really worth emphasizing, this project absolutely would have got nowhere without being deeply multidisciplinary. We absolutely needed people who really understand deep learning and can innovate in novel, challenging deep learning architectures. We equally need people who understand density functional theory. We cannot possibly do this without world-class experts in density functional theory. We also need world-class experts in wave function theory to generate that training data. Then we need great engineers, because this is a big engineering problem. We're using a lot of compute, we need to use it efficiently, the whole thing needs to be scalable. We need program managers to manage all of this complexity, including external partnerships and so on. So a big thank you to the team, but a real call out for the fact that this project, in my view, could never happen without an environment in which people can work across disciplines very, very closely together. So they're published on arXiv. Because the calculation, the creation of this training data set was so complex and subtle, there's a separate paper just on the creation of the training set. So I encourage you to look at those papers. I really am almost done. I'm going to finish, I'm afraid, with a shameless plug. If you wanted to learn more about anything that we've talked about there, not so much on the quantum physics side, but on the machine learning side, the no free lunch theorem, diffusion models, and so on. This book, it's free, it's available, bishopbook.com, freely available. If you like me, you like physical old-fashioned books as well, this is contractually, Springer must produce this in what's called stitch signatures. This is produced, Gutenberg would have been proud of this, right? This is a beautifully produced book. It opens flat and it's going to last for years. Beautifully produced book. If you do buy that on Amazon, please leave a nice review. And I'm very proud that this was Springer's most successful book of 2024, but even more proud of the fact that it was written jointly with my son. So with that, thank you all for your attention. Thank you.
Thank you very much, Chris, for the very interesting talk. I was open for questions.
It's not a question, just the book is actually very good, so it's I use it to teach and it's fantastic, particularly apart from transformers.
Thank you. That wasn't planted, by the way, that was...
Can you comment on uncertainty quantification? I mean, you probably don't need it for the Scala model, but in general.
Right. I think, let me give you a rather general answer to that. I know that's one of the themes of the week. I think this is really one of the big challenges in machine learning in general and of enormous importance, I think especially in the scientific domain. Because if you have uncertainty, if you have good uncertainty quantification, you can drive active learning. And we're always looking for ways to do active learning. So instead of generating 150,000 molecules, a huge expense and cost, taking a couple of years, then use it for training. It'd be so much smarter to start with a smaller data set, train a model, then understand where the model, if the model could say, I'm really confident over here, but I'm much less confident over there, great, we know to go and generate more data where it's less confident. So if we have, if this is what you meant by uncertainty quantification, if the model can not only make a prediction, but give you a confidence, a calibrated confidence in the accuracy, that would be extremely valuable. It's almost as valuable as the prediction itself because it tells you where to go and generate more data. You might even get, I don't know, maybe an order of magnitude efficiency in data generation. And when you're pushing the limits of compute in terms of what you can afford to do in terms of data generation, when the data is scarce, when the data is so valuable, the ability to do that active learning, I think would be really powerful. So it's an incredibly important topic, and I think it's wide open for research. So I'm glad that it's one of the themes of this week's workshop. Yeah.
Thanks for the nice talk. You opened by describing the ability to predict the natural world of mathematics as one of the greatest scientific discoveries. This seems like something that's eluded machine learning up until now, at least. We use ML in all sorts of scientific pipelines for making predictions, but we haven't been able to use machine learning to discover new mathematical equations that can provide us with a better understanding of the universe. What's beyond quantum mechanics, for example, or even recovering what we already know to any reasonable extent. Is this something that you've thought about? Could this be the sixth paradigm? How might we try to approach that?
Yeah, that's a super interesting question. It is something I've thought about a little bit, but it's not, the focus of what my team does are these deep physics models. But there is a major paradigm shift happening right now, of course, which is AI, and it's extraordinarily powerful. I was fortunate to be given very early access to GPT-4, long before it was still super secret, and I remember the first time interacting with it, like the hairs on the back of my neck went up. It was like the first time I've actually interacting with something that I could even vaguely begin to call intelligent, right, in some true sense, whatever that means. And then progress since then has been extraordinary. So the other place where deep learning is going to revolutionize science, something I haven't talked about, is through the power of large language models to help accelerate the scientific discovery process itself. So think about, you're going to say, right, I'm going to invent a room temperature superconductor. Where are you going to start? Well, a good place to start is to read every paper ever written about superconductors of every kind, right? That's pretty tough for a human being to do. But the Copilot can do that, the AI can do that, and then you can interact with it. Now you're going to say, okay, maybe we need some ideas, all right? Well, how are we going to do this? Again, the LLMs are great at suggesting ideas. They can be great at filtering ideas, filtering out good ones and bad ones. They can help with that experimental design. They can maybe help with the actual conducting experiments. So first of all, they're computer experiments, and I believe in the future more and more of this experimentation will happen in the computer. But should I be testing my hypothesis by running an expensive first principle simulation, or should I run a much faster emulation that may or may not be confident in the region I'm interested in? Or should I suck up the expense and the time cost of actually doing an experiment in the lab? How do I weigh up the results? Now I get my results back, how do I incorporate those into my hypotheses and go around that cycle? This kind of AI technology can help at every single stage of that, including lab automation, running 1 million experiments in parallel and all the rest of it. So that will be transformational. And I've not really touched on that. But if we now think about, would somebody be standing here in the Newton Institute in the next few years announcing a new piece of mathematics that was discovered with the help of, or even largely by, a deep learning system, an AI system? Yes, it's possible. But I think that will be more on that side of the larger language models, the reasoning models that will help with that process. I think the role of things like Scala or the other systems I've talked about are tools that will be called by those systems. So those scientific discovery engines will need to call tools. The tools might be a wet lab, they might be a computer simulation, but these kinds of tools, these kinds of computational tools, these emulators, will not only accelerate scientific discovery in the way that I've described, but because they can be called now in a kind of an automated way, in a massively parallel way, they very much complement what I think we'll see the large language models and the agentic reasoning systems do. So I think there are really these two kind of revolutions unfolding in parallel, and they very much complement each other. That's my guess.
So you describe how mathematics is really good at explaining physics and chemistry, but if you go into biology, it's a lot less successful. Things are less deterministic. Have you got any thoughts on how the ideas you've been talking about could be used in biology and healthcare and such like, where things get a little less deterministic, a little less predictable?
It's great. So my team sort of starts from the physics end, but we then see how far we can push that, and you can push it a lot further than you might imagine. We had a paper published in Nature within the last 6 months, fairly recently, called AI squared BMD. It's a catchy name. It's sort of AI accelerated ab initio biomolecular dynamics. It's a bit of a mouthful, but if you want to understand the heart of biology is the idea that DNA defines proteins, that DNA is transcribed into RNA and then translated into proteins. Those proteins then fold into some three-dimensional structure. That three-dimensional structure determines the function of those proteins, including interacting back with the DNA. But it's actually a dynamical process. So proteins aren't a single fixed static structure. They're dynamical. They can open and close, like the spike protein on SARS-CoV-19, for example, opens and closes, and that changes its ability to invade the cell. So we need to be able to model the dynamics of what's going on. It's all about the, as Feynman called it, the wigglings and jigglings of atoms that define biological function. And you can get remarkably far. We can do first principles biomolecular simulation with proteins having thousands of atoms. And that's done by really embracing that fifth paradigm. So thinking about how to do a sort of coarse graining, thinking about groups of atoms rather than individual atoms, modeling the interactions between those using density functional theory, conventional density functional theory, and then building an emulator of that interaction between different pieces of protein. That force field now is going to get called millions and millions of times. So it's got to be really fast. You can't solve the Cohen-Sham equations every time. You've got to have that emulator. With that emulator, we can now do molecular dynamics at a much larger scale than any of us thought was possible. We're actually trying to push that even a stage further and to say, we don't actually really care about the individual jigglings and wigglings of individual atoms. What we want to know is, what are the different shapes the protein could have, and what's the probability of being in those different shapes, and what's the rate of transition between them. In other words, we want to know about that distribution. We don't, modelling the actual dynamics is just a means to an end, a very, very compute expensive one. Can we go directly to the distribution? So we have a project called the Biomolecular Emulator, which is really trying to even go a stage further and very efficiently go directly to that distribution. It published its first paper a few weeks ago.
Maybe one final question before we thank Chris?
No.
So just a general question. Don't you think that it will be very difficult for, in academia, in the academic world, to gather groups like you have, and in Microsoft, with all the possibilities that you have, in the sense that, yeah, it's very difficult currently to get the same amount. I'm not talking about compute power, but I'm talking about gathering big teams, and I am on one side very enthusiastic with your talk and your ideas, but I am wondering how can we extend and propagate this if only a few, like a few big companies, well, excellent in the way, but we're able to do this. I mean, of course, we are living a shift here in science due to AI, it's not obvious for me how classic way of thinking science and even founding new teams, new projects. And have you some thoughts about that?
It's such a great question. Often the question is formulated in terms of compute. You
Yeah.
ruled out compute. You're talking about how to build teams. I feel very strongly about this. This is something. If you look at the history of 28 years ago when I came to the Newton Institute and I joined. It was the exact day that I started here, the 1st of July, was the same day that Microsoft opened its first research lab outside the US. It happened to be in Cambridge, so I joined them pretty soon after that. And in those days, we functioned a lot like academia, where everybody was a principal investigator, and you had postdocs and interns and so on, and there were lots of small projects. And I've always been a fan of just going after one or two really big things, and really, that requires bigger teams, that requires cross-disciplinarity. Given that you've put aside the compute question, I see no fundamental reason why the academic world can't get together. I can see that there are, maybe the incentive structures are wrong, maybe they need to be rethought, but I think it's a tremendously important question. I think what mechanisms are there to incentivize and allow people to come together, especially in multidisciplinary teams? I was a research professor for 5 years, and the research councils would try hard. They would say, we have an interdisciplinary program. This funding is only for biology meets physics or something. But the temptation is to write a joint proposal, get the money, split it, go your separate ways, and carry on as before. So it's not that people aren't aware of this or haven't tried. I think it's a very difficult problem, but I think it's just tremendously important, and I think we have to think of creative ways. There's something the Newton Institute called. The Newton Institute's a great convener, a great way of bringing people together in the mathematical sciences. Really thinking about cross-disciplinarity, because it really is crucial for going after, especially AI for science. You have to have at least those two disciplines of machine learning and deep science, and we can only ever know something about one of them and be rather amateurish in the other. It's very difficult to have deep expertise in both, so you do need those teams of people. So I don't have the answer, but I love the question. I'd love to brainstorm with you how we might help with that. I should say, by the way, that part of this Scala project involved an academic collaboration, and we would have struggled to do that without that academic expertise, because even though we build these larger multidisciplinary teams, even then we can't always have all that deep expertise in-house. We want the very best people. So there's, in many cases, there are collaborations with the academic world that play a role. But yes, I think there is scope to think beyond the many small projects and the many small principal investigators and think about how to incentivize larger teams. By the way, I think one of the reasons this team is so successful is I can't tell you who the PI is. It's a set of people who are passionate about working together to go after a really big problem.
Thank you very much.
Thank you. Great question. Thank you.
Let's thank questions.